It's wonderful to be here, and I'm delighted to share with you the work that we're doing in Oxford, but more broadly, what engineering and a multidisciplinary approach can bring to trying to crack cancer. What I'd like to start by doing, though, is explaining what on earth a mechanical engineer is doing here talking about cancer. It's quite a good question because, aged 18, this was my plan. I wanted to design Aston Martins. That's why I did mechanical engineering. And how I got into biomedical engineering was complete chance. I was doing my final year project on ultrasound imaging, but it was ultrasound imaging in oil pipes. And we were having a terrible problem with bubbles that kept floating through our pipes and messing up our images. And by pure chance, my supervisor happened to be talking to the new head of radiology in London, who said, "Oh, we're using bubbles, so we use them in imaging as well. Yeah, they are quite a problem. Why don't you get your student to look at that?" And to cut a long story short, that became my PhD because I considered trying to image the human body considerably more interesting than oil pipes. So to explain how bubbles come into this, we need to go back a few decades. They've now been used in medical imaging for some time, but this is back in 1969 when ultrasound was a new and sexy imaging modality. It had only just come online. But they didn't have very good ways of improving the image quality. They weren't great. And what they noticed was this chap, Dr. Gremiak, and he was doing an ultrasound scan, and he was simultaneously injecting a dye into the heart to see how much was going through and whether the heart was working correctly. What he noticed was that every time they injected the dye, the image lit up really brightly, and you could see how the heart was pumping. About 5 years and 10 patents later, they worked out, unfortunately, it wasn't a magical property of this dye. It was actually due to bubbles. Bubbles were being formed at the tip of the syringe. They were washing into the heart, and it was these bubbles that were improving the ultrasound scan. Now, before anyone has serious concerns if they're a scuba diver, it is actually safe to inject bubbles into the bloodstream, as long as they're small enough. This is an image here. We have a red blood cell, we have a white blood cell, very important for immunotherapy, which we'll talk about later, and a platelet. So these are already washing around in the bloodstream, and this is the bubble, so it's very, very tiny. And as long as they're sufficiently small, they can pass safely through the bloodstream. Bubbles are full of gas, so they're very, very squishy. When they're hit by ultrasound, they start to oscillate, they start to expand and contract, and they produce these very, very strong ultrasound echoes. And so what was happening was all of the bloodstream was lighting up, and the doctors could see what was happening, and it was massively improving their ability to form a diagnosis. What I became interested in, though, was whether this could be taken forward and used for therapy instead. So not just for imaging, but to actually use these tiny bubbles as vehicles for treatment. Because we have this little structure, we can use it to encapsulate drugs. Because the bubbles are so tiny, we actually need to put something on their surface to stop them falling apart. And that's normally a biocompatible polymer or surfactant, actually stuff that's naturally present within the body. So we form this little capsule into which we can attach drugs. We can also stick things on the surface of the bubble that will get it to bind to, for example, the site of a tumor. So we can stick the bubbles in the right place, and we can then use ultrasound to oscillate these bubbles to deliver the drug at a specific point. So we can control when and where that drug gets delivered. Now that's very powerful because it means we have a way of targeting the therapy. And the very obvious target for my future work was cancer. I also want to talk a little bit about that. Why do we need all of these new immunotherapy, these amazing drugs that have been developed in the last 20 years? And to do that, I need to say a little bit actually what cancer is. And essentially, it's a programming error. All our cells contain DNA, which controls how our cells reproduce. And in healthy tissue, that's a very well-regulated process. Cells divide, keep dividing, and if something goes wrong, if the DNA becomes corrupted or they're injured in some way, that cell is taken out by the immune system. There's actually programming within the DNA, a process called apoptosis, which means the cell dies. And then an immune cell will come and remove the debris. Nothing's wrong. The cells can continue to replicate safely. What happens in cancer is that scrambling of the DNA switches off that programmed death. So if the cell gets injured, it carries on replicating. And this is what happens when a tumor forms, is these cells start to replicate in a completely uncontrolled fashion. They form a growth, And eventually, unfortunately, we end up with a tumor, continues to grow, and eventually just chokes off the rest of the system. And unfortunately, that's usually what happens. Is it's not the tumor that kills you, it's the fact that it stops your heart, your lungs, your brain from functioning. Now, why is this so difficult to treat? Well, the reason is they're our own cells. It's not a foreign virus or a bacterium that our immune system will recognize immediately and take out, and it's not something we can easily design drugs to target. They're our own cells. We're going to harm healthy tissue when we try and treat it. As Ben's already described, it's not that the immune system doesn't work. The immune system does actually recognize that the DNA has become scrambled, but cancer cells will release certain chemicals that shut down that response. So when you open up a tumor, they're frequently full of these immune cells, but they've stopped working. Sadly, it's even more challenging than that. Because of the way the tumor develops, there are a number of reasons why it's very, very difficult to get a drug in there. The first is the network of blood vessels that you have within the tumor. So again, in healthy tissue, we have this very well-ordered structure. There's nice blood supply, oxygen, nutrients, everything gets through to the tissue. In a tumor, because it's growing so fast, that vessel network gets disrupted. It's very chaotic. There are big gaps between these tiny little blood vessels, which means that a lot of the tumor doesn't receive enough nutrients, doesn't receive enough oxygen. And if we put drugs into the bloodstream, they simply don't get to all of the tumor. So it's very difficult to treat. The second problem, in addition to a blood supply to tissue, we also have a system called the lymphatic system that's essentially the drainage for the body. And again, this tumor grows very, very fast. It chokes that off. And what that means is we develop a very high pressure inside a tumor that again stops drugs from getting inside. I also mentioned this large gap between the vessels. Oxygen just simply cannot diffuse into the tissue. And something very weird happens if you deprive cells of oxygen. They sort of turn into zombies. So they're half alive, but they're in this sort of sleep mode, and they don't respond to almost any form of therapy. They don't respond to drugs, they don't respond to radiation, they actually don't respond to immunotherapy either. So we have these low oxygen regions that are very, very difficult to treat, and that's often where you get recurrence happening. And then finally, one of the other things that this low oxygen state does is it makes the cancer very aggressive. Cells tend to break off and migrate to other areas of the body, forming secondary tumors. And sadly, it's often the secondary tumors that turn out to be fatal. So we have these 4 challenges to deal with. We can't get the drugs in, and if we do get the drugs in, they may not work. It's clearly not all doom and gloom. We've heard about people surviving cancer. There are many effective treatments, provided we can catch them early enough. The first recorded cancer treatment is from 2000 BC, where there's an Egyptian papyrus that describes the use of a hot knife to remove a malignant growth. And pretty much for the subsequent 4,000 years, that's been the main treatment, and it's still our first line of defense, surgery. If you can take it out, it's probably the best we've still got. End of the 19th century, radiation. We had a less invasive way of potentially treating tumors, often in combination with surgery. And since then, we've added lasers, we've added microwaves, we've added radiofrequency ablation and focused ultrasound as other ways of complementing this. This is in the 1930s, moving through to the 1960s. And as we've heard, this is pretty much where we are today. We have our lines of defense: surgery, radiation, chemotherapy. The advent of chemotherapy was the first time we had a chance of treating these secondary tumors, these metastatic tumors. The problem with chemotherapy is it involves giving a drug to the entire system. We are trying to catch individual cancer cells in many cases of very, very tiny tumors, but it's less than 1%. It's a fraction of a percent that will actually make it into the tumor. The rest of that drug is going into healthy tissue. Ben's already described, these things came from mustard gas. They are very, very toxic drugs, and that's why we have these horrendous side effects associated with cancer. So where's it going? Well, as we've heard today, immunotherapy is probably one of the most exciting developments of the last 30 years in science, let alone in medicine. It's incredible. I think it's going to transform the way that we think about treating cancer. We've still got a little way to go, though. At the moment, the cost is eye-watering. It really is for trials, so the numbers of patients that can receive this is limited by that. The side effects are also horrendous. I have a colleague who unfortunately underwent this, and he said it makes the side effects of chemotherapy look like a picnic. Other problem is the real successes have mainly been in leukemia, in blood cancer, and in skin cancer, for the simple reason that they're accessible, and not all tumors are equal. We still have our 4 problems that I mentioned before. It's difficult to get the drug into the core of a tumor. So where you have a solid tumor, for example, in pancreatic cancer, in brain cancer, they're much harder to treat. And that's where I think engineers can come in and be useful. What do engineers do? We analyze systems and we come up with solutions. We're not biologists, we're not oncologists, but we can look at problems and come up with delivery solutions, because essentially treating cancer is a delivery problem. One really lovely example of where a multidisciplinary approach can come in is something called photodynamic therapy. So this uses drugs which only become toxic when they're exposed to light. So you can distribute them throughout the body, but they won't do anything until you shine a laser on it, which means you don't experience these very toxic side effects. The downside to this, though, is clearly that light doesn't penetrate very well into the body. It will only go a few millimeters. And the other problem is, when a patient is given these drugs, they actually need to be kept in a dark room for several weeks, because clearly if they go out in the sunlight, the entire drug is going to be exposed. So it's very exciting, it has some limitations. A really cool thing that's happened in the last 5 years is the discovery that ultrasound can be used to excite these drugs as well. And they can actually now make drugs which are only ultrasound responsive. So you can go out into the light. We don't have very much ultrasound out in the environment, so it's fairly safe. And ultrasound can penetrate much deeper into the body. This is a really nice example of where a discovery in physics produced a change in oncology. And this is just an example in skin cancer where the tumor has been completely removed. But it's still not addressing this delivery problem. Again, most of these applications have been in tumors that are quite easy to get at. Another area that's been very, very well explored in the last sort of 20 years is the use of nanotechnology, so putting drugs into particles to penetrate into tumors. The main theory behind this is that because you have this very chaotic vessel structure that I mentioned within a tumor, and not only are the cells replicating very quickly, but actually the vessels themselves are growing very, very quickly. And as a result, they're quite leaky. So the spaces between the cells lining the vessels are pretty large. And it's a little bit like having a sieve where the rest of the healthy tissue is nice and tightly packed. And the idea is that if you put your drugs into particles of just the right size, they'll be able to escape into the tumor, but they won't escape into the healthy tissue. Now, this is really exciting, and someone mentioned earlier that we have, 17 papers an hour we'd have to read to keep up? Well, an awful lot of those papers, I'm afraid, have been due to this approach. There is a ridiculous number of papers on nanotechnology. Would anyone like to hazard a guess as to how much more drug we're able to get into a tumor using this approach? So I said it's less than 1% with conventional chemotherapy. This was a paper that caused a bit of a stir in Nature about 18 months ago now. Yeah, not great. 0.7%. So was this actually not much of an improvement on the state of the art? Why? Well, the simple reason was there's this back pressure. It doesn't matter if the holes are the right size. If there's something pushing back against it, the particles are not getting delivered. But we don't want to lose hope. Again, this is where bringing in elements from physical sciences can potentially help. We just need to give these particles a bit of a push. One very simple way of doing that is using a magnet. We're very good at making magnetic nanoparticles. We use them in imaging all the time. So we can use an external magnetic field to actually drag particles into a tumor. These are some from our lab. This is just using a very simple, literally a permanent magnet to pull them into a tumor. But this is some really cool stuff from a lab in Zurich from Brad Nelson's group. He's made a micro swimmer, and by applying an oscillating magnetic field, we can make this little particle actually move and literally swim through the tissue to drag drugs into a tumor. Now this is at the micro scale. Last year's Nobel Prize for Chemistry was won by a team who've taken this down to the molecular level. So this is developing delivery systems that exploit the gradients, chemical gradients within a tumor, so that the drugs will literally swim along and actually be sucked into the tumor. So we no longer have this diffusion problem, we have an active delivery approach. This is probably 10, possibly 15 years away still. But again, this combined with the developments in immunotherapy, I think is going to be game-changing. Another approach, and most of the work that we do in Oxford, uses another physical stimulus, and this is ultrasound. So coming back to where I started out, ultrasound is just a pressure wave, and it carries energy through tissue. That's how you can hear me when I'm talking. We're using that to carry drugs. Now we can give that a little boost by using bubbles. So they're coming back. What bubbles do is they act as tiny loudspeakers. We drive them with an ultrasound field. We get this oscillating motion. And if we look at what happens to the fluid around the bubble, this is what we see. So because of this pumping effect of the bubble, we're actually able to push drug, circulate it around, and get it deeper into the tissue. And just to give you an idea of scale, this is 5 micrometers, so 5 millionths of a meter, smaller than a red blood cell. But it's able to push stuff around 100 times over that distance. So we can easily push it deep enough into a tumor to be effective. Now, this is in a dish in the lab. Much more interesting to actually see what happens in a real tumor. So this is a colon tumor. What you're looking at, the blue here are the cancer cells. The red, you can hopefully just see the blood vessels that are penetrating through it. And drug is green. Now, this is what happens when we try and deliver the drug with no ultrasound, with no help. This is an immunotherapy drug. It's an antibody. And what we see, if we look at 3 different regions of the tumor, near the blood vessel, we get plenty of drug. Out towards the periphery and deep in the core of the tumor, nothing. It just doesn't get far enough. And that means this is not going to work. We simply can't get enough drug throughout the tumor to be effective. We repeat this, but now we use bubbles and ultrasound to push that drug deeper into the tumor, and we see green everywhere. And this is something which one of my colleagues will hopefully be taking forward to a clinical trial within the next couple of years in Oxford. So we're getting there. We found a way of overcoming this problem with a chaotic vessel structure, the fact we need to push drugs over a greater distance, and overcoming this internal pressure. We've still got low oxygen concentration and secondary tumors to worry about. The reason bubbles are amazing is they give us an immediate way of addressing that oxygen problem because we can simply fill them with oxygen. So we can actually deliver that simultaneously with the drug, temporarily reverse the low oxygen state within the tumor to make the drugs work better. This is some work we've been doing with a group in Northern Ireland who've developed, again, one of these ultrasound responsive drugs. This is looking at a pancreatic cancer tumor. And as you see what happens, in 5 days, these things double in volume. It's an incredibly aggressive form of cancer. Together with glioblastoma, it's one of the 2 ones for which the prognosis has just not improved in 50 years. If we give the drug with no ultrasound, nothing happens. It's not toxic. It doesn't do anything. If we deliver it with a normal microbubble, so not containing oxygen, we see a little bit of an effect, but because these tumors are very, very aggressive, it starts to grow very, very quickly. But we deliver it with oxygen, we can actually halve its volume and it stays down. And we've shown subsequently that with repeat treatments, we can pull that down further. That's the difference between a surgeon being able to perform an operation or not. So this is quite a big deal. And again, this is something we're working very hard to get into the clinic within the next couple of years. More recent stuff we've been doing with the same drug is adding in that magnetic targeting that I mentioned. So now we magnetize our microbubbles so that we can get a higher concentration within the tumor. And what you're seeing here is a plot of a marker that we take out of the tumor that tells us whether we've actually successfully killed the cancer cells. Because actually the size of a tumor doesn't necessarily tell you the whole story. Tumors can get absolutely huge due to an immune response. What we need to look at is the detailed biology of the tumor to see whether it's worked. And what we were delighted to see here is that where we use the magnet to concentrate our drug, we see this very, very high concentration of these markers that means the tumor's dead. The question I get asked probably most often, and absolutely justifiably, is when? When is this going to be available? My brother, my sister, my father, my mother suffering from cancer, can they have this treatment? I say we are working incredibly hard to be able to make that answer yes, but it's fair to say that a lot of what I've talked about today is still quite a long way down the line. And that's because it's not just the science that needs to be sorted out. Yes, engineers need to work with physicists, with chemists, with pharmacologists, with medics, with oncologists and biologists, but we need a much bigger team than that. There are a whole lot of barriers in taking development from the laboratory through to the clinic, let alone worldwide. We still have some key scientific challenges. I said the DNA gets scrambled. I didn't say why, for the simple reason we don't know. And I imagine most of us have got a relative or a friend who smoked 60 cigarettes a day, drank like a fish, and lived healthily till they were 100. Others who did everything right still got cancer. We don't know, and we need to. We need to understand what is the combination of genetic and environmental factors that affect that. We need to know why some drugs don't work for some people. And we need to understand a heck of a lot more about the immune system. On the more engineering side, we need to make these treatments efficient. I've shown you some exciting data, but we need to make sure that works every time. We need to make sure that the drug gets throughout every tumor consistently. And we need effective ways of monitoring it. We need to have cost-effective, convenient imaging that allows this to become a widespread approach. And this is where it gets really difficult. These things cost an absolute fortune. The old standard was it takes 10 years and £10 million to get a new drug into the clinic. If you're talking about immunotherapy, you're adding a naught, if not two, to that cost. It's eye-watering how much these things cost. And that's a combination of the science, but also just getting through the regulatory process. Yes, it should be rigorous, but it needs reviewing, because at the moment, it's just a roadblock. Similarly, the cost of manufacturing and the way that the healthcare systems work, the way we pay for these things, is also unbelievably complicated and actually, in my opinion, stifles innovation. I also don't think it's the whole story. What I'd really like is for all of the treatments I've been talking about to become completely redundant because we don't need them in the first place. And one thing for that is coming up with better ways of detecting cancer as early as possible. Why? Because it increases the chances of survival by orders of magnitude. Prostate, breast, ovarian cancer, we can now actually often cure, provided we catch it early enough. The reason pancreatic and many brain tumors are so lethal is simply they're just not diagnosed early enough when a treatment could be effective. That needs to be sorted out. We probably can't afford to give every single person an MRI scan every year in the hope that we might catch something. But there's been some incredibly exciting work coming out of Boston recently where they're developing tests, simple blood tests that can detect early tumor markers really, really early to send patients for that full body scan. And that's what we need. We need a lot of innovation in the area of early detection as well, so that the treatments aren't needed. Even more than that, education. A lot of the infectious diseases that were the major cause of death 100 years ago were not eliminated by amazing drugs. They weren't eliminated by extraordinary imaging techniques. They were eliminated by sorting out the water supply, sewage system, and getting people to wash their hands. And actually, we need to look at how cancer can be prevented through education, through changes in lifestyle, through changes in our environment, so that this doesn't become a problem in the first place. Now, we all know that if we exercise daily, we eat properly, we limit our drinking, stop smoking, we probably reduce our chances of cancer. For some reason, we don't do it. Education needs to be sorted out. The other thing, though, is there are things we can't control. We can't control the use of antibiotics in our agriculture system or the use of pesticides. when we buy stuff in the supermarket, we trust that it's healthy. But a lot of work needs to go on actually across the board. Engineering, architecture, politicians, agriculture, all of it needs to be integrated to limit our exposure to pollutants. It all needs to happen. I've deliberately put these jigsaw pieces separately because I don't think we're there yet. But I'm delighted to be part of this initiative because I think that's what's going to put these together. Thank you very much.